Welcome to a journey through the cosmos unlike any other. Today we're going to explore the most haunting, beautiful, and scientifically fascinating places in our universe. Galactic graveyards. These are the final resting places of stars, the remnants of cosmic violence, and the birth sites of new celestial wonders. Over the next several hours, we'll traverse the darkness between dying suns, witness the aftermath of stellar catastrophes, and discover what these cosmic cemeteries tell us about the past, present, and future of our universe. When we look up at the night sky, we see points of light that seem eternal and unchanging, but the universe is anything but static. Every star we see is on a journey from birth to death, and scattered throughout the galaxies are the remains of countless stars that have already completed that journey. These stellar graveyards aren't places of sadness or ending, though. They're crucibles of transformation, where the elements that make up everything we know, including ourselves, are forged and scattered across space. Let's begin our journey by understanding what we mean by galactic graveyards. These aren't physical locations with boundaries or markers. Instead, they're regions of space populated by the remnants of dead and dying stars. They include planetary nebulae, supernova remnants, neutron stars, black holes, and the diffuse clouds of gas and dust that represent all that remains of ancient stellar generations. Each type of remnant tells a different story about how stars live and die. Together, they paint a picture of cosmic recycling on a scale that's almost impossible to comprehend. The story of galactic graveyards begins with stellar birth. Stars are born in vast clouds of gas and dust called molecular clouds or stellar nurseries. These clouds can be hundreds of light years across and contain enough material to form thousands or even millions of stars. Gravity pulls the gas and dust together, and as the material compresses, it heats up. Eventually, if there's enough mass, the core becomes hot and dense enough for nuclear fusion to begin. Hydrogen atoms fuse together to form helium, releasing tremendous amounts of energy in the process. A star is born. But from the moment of its birth, a star is engaged in a constant battle between the outward pressure of fusion and the inward pull of gravity. For most of a star's life, these forces are in balance. This stable period is called the main sequence, and it's where stars spend the majority of their existence. Our Sun is currently in its main sequence phase and has been for about 4.5 billion years. It will remain there for another 5 billion years or so before its fuel begins to run out. What happens when a star exhausts its hydrogen fuel depends almost entirely on its mass. Low-mass stars like our Sun swell into red giants, fusing heavier elements in their cores before eventually ejecting their outer layers and leaving behind a white dwarf. More massive stars go through multiple phases of fusion, creating increasingly heavy elements in their cores before ending their lives in spectacular supernova explosions. The most massive stars can collapse into neutron stars or black holes, objects so dense and strange that they challenge our understanding of physics itself. Let's start our exploration with one of the most beautiful types of galactic graveyard, planetary nebula. Despite their name, planetary nebulae have nothing to do with planets. When 18th century astronomers first observed them through primitive telescopes, the round, disc-like shapes reminded them of planets, and the name stuck. In reality, planetary nebulae are the ejected outer layers of dying stars, illuminated by the intensely hot stellar core left behind. When a star like our Sun exhausts the hydrogen fuel in its core, it begins to fuse hydrogen in a shell around the core. This causes the star to expand dramatically, becoming a red giant. The star can grow so large that if our Sun became a red giant, it would engulf the orbits of Mercury and Venus, and possibly even Earth. The outer layers of the star become loosely bound and unstable. Eventually, the star begins to pulse, ejecting its outer envelope in waves. These shells of gas expand outward into space at speeds of tens of kilometers per second. What's left behind is the hot, dense core of the star, now exposed to space. This stellar remnant, called a white dwarf, is incredibly hot when first exposed, with surface temperatures that can exceed 100,000 degrees. The intense ultraviolet radiation from the white dwarf ionizes the expanding shells of gas, causing them to glow in brilliant colors. Different elements emit different colors when ionized. Hydrogen glows red, oxygen glows green or blue, and nitrogen glows red or orange. The result is a celestial light show of stunning beauty and complexity. Planetary nebulae come in an astonishing variety of shapes and structures. Some are simple spheres or ellipses, but many have complex, intricate structures with multiple shells, jets, knots, and filaments. Some look like hourglasses or butterflies. Others resemble eyes staring out from the depths of space, which is why one of the most famous planetary nebulae is called the Helix Nebula, or the Eye of God. The complexity of these structures tells us that the death of a star is not a simple, uniform process, but involves multiple episodes of mass loss, rotation, magnetic fields, and possibly the influence of companion stars. One of the most famous planetary nebulae is the Ring Nebula in the constellation Lyra. Through a small telescope, it appears as a perfect smoke ring in space, about 1 light-year across. But detailed images from space telescopes reveal that the ring is actually a cylinder or barrel shape that we happen to be looking at end on. The nebula is expanding at about 20 kilometers per second, and based on its size and expansion rate, astronomers estimate it formed about 6,000 years ago when the central star ejected its outer layers. Another spectacular example is the Cat's Eye Nebula, one of the most complex planetary nebulae known. It consists of multiple concentric shells and arcs, along with high-speed jets of material shooting out from the central star. The complexity suggests that the star went through multiple episodes of mass loss, possibly influenced by a companion star orbiting the primary. The nebula also shows a series of 11 or more concentric rings extending far beyond the bright central region, suggesting that the star has been losing mass in pulses for thousands of years. The Butterfly Nebula, also known as the Bug Nebula, shows 2 distinct lobes of material spreading in opposite directions from the central star. The lobes are expanding at speeds exceeding 600 kilometers per second, making this one of the fastest planetary nebulae known. The distinctive shape is thought to result from the presence of a dense disk of material around the star's equator, which forces the ejected material to flow preferentially along the star's poles. The result looks remarkably like wings of a butterfly or the body of an insect, giving rise to the nebula's common names. Planetary nebulae are relatively short-lived phenomena in cosmic terms. The expanding shells of gas become increasingly diffuse over time as they spread out into the surrounding interstellar medium. After about 10,000 years, most planetary nebulae have faded below visibility, their material scattered and mixed with the general interstellar gas. The white dwarf at the center gradually cools over billions of years, eventually becoming a black dwarf, though the universe is not yet old enough for any white dwarfs to have cooled to this stage. The material ejected by dying stars like this is crucial to the chemical evolution of galaxies. Stars are cosmic factories that create heavy elements through nuclear fusion. The hydrogen and helium that made up the original star came from the Big Bang, but during the star's life, it fused some of that hydrogen into heavier elements like carbon, nitrogen, and oxygen. When the star ejects its outer layers to form a planetary nebula, it enriches the interstellar medium with these elements. Future generations of stars will form from this enriched material, and they'll contain higher proportions of heavy elements than their predecessors. Now let's turn our attention to a far more violent type of stellar death, the supernova. While planetary nebulae represent the gentle passing of low to moderate mass stars, supernovae are the catastrophic explosions that mark the deaths of massive stars. These events release more energy in a few weeks than our Sun will emit over its entire 10 billion-year lifetime. For a brief period, a single supernova can outshine an entire galaxy of hundreds of billions of stars. The path to supernova begins when a massive star, one with at least 8 times the mass of our Sun, exhausts its nuclear fuel. Unlike lower mass stars, massive stars can fuse elements beyond helium. As each fuel source is depleted in the core, the star contracts and heats up until it's hot enough to fuse the next element in the sequence. After helium comes carbon, then neon, then oxygen, then silicon. Each stage of fusion happens faster than the last. A massive star might spend millions of years fusing hydrogen, 1 million years fusing helium, a few thousand years fusing carbon, and less than a day fusing silicon. The end comes suddenly and dramatically. When the star tries to fuse iron, the process requires energy rather than releasing it. Iron is the most stable element, meaning it takes energy to either fuse it into heavier elements or split it into lighter ones. Once a star's core is primarily iron, fusion stops. With no outward pressure from fusion to counteract gravity, the core collapses catastrophically. The collapse happens so quickly that the inner part of the core reaches relativistic speeds, a significant fraction of the speed of light, in less than a second. The core collapses until the protons and electrons are squeezed together, forming neutrons. The collapse is halted when the core reaches the density of an atomic nucleus, about 100 trillion times the density of water. The infalling material rebounds off this incredibly dense core, generating a shock wave that propagates outward through the star. The shock wave is initially stalled by infalling material, but neutrinos streaming outward from the core and turbulent convection reinvigorate the shock, allowing it to continue outward through the star's layers. When the shock reaches the surface, the star explodes in a brilliant supernova. The explosion ejects most of the star's mass into space at speeds of thousands or even tens of thousands of kilometers per second. The ejected material plows into the surrounding interstellar medium, creating an expanding shell of hot, shocked gas. This expanding shell is called a supernova remnant, and these structures are some of the most spectacular and scientifically important objects in the galaxy. Young supernova remnants are hot and bright, shining in X-rays as well as visible light. The Crab Nebula is perhaps the most famous supernova remnant. It formed from a supernova explosion that was observed by Chinese, Arab, and Native American astronomers in the year 1054. The supernova was visible in daylight for 3 weeks and remained visible to the naked eye at night for almost 2 years. Today, the Crab Nebula is a complex, filamentary structure about 11 light-years across and still expanding. At its center is a pulsar, a rapidly spinning neutron star that rotates 30 times per second, emitting beams of radiation like a cosmic lighthouse. The Crab Nebula is powered by this pulsar. As the neutron star rotates, it generates a powerful magnetic field and accelerates particles to nearly the speed of light. These particles emit synchrotron radiation across the entire electromagnetic spectrum, causing the nebula to glow. The pulsar also drives a wind of particles into the surrounding nebula, creating shock waves and maintaining the nebula's distinctive wisps and knots of glowing material. Without the pulsar, the Crab Nebula would have faded significantly over the past 1,000 years. Another spectacular supernova remnant is the Veil Nebula, part of the larger Cygnus Loop. This remnant is much older than the Crab Nebula, having formed from a supernova explosion that occurred between 5,000 and 8,000 years ago. The remnant is enormous, stretching over 3 degrees across the sky, about 6 times the diameter of the full moon. The beautiful, delicate filaments of the Veil Nebula trace out the shock front, where the supernova blast wave is still plowing into the surrounding interstellar medium. The different colors in the nebula come from different ionized elements: red from hydrogen and sulfur, green from oxygen, and blue from a mixture of hydrogen and oxygen. The Tycho supernova remnant is another well-studied example. This remnant formed from a supernova observed by the Danish astronomer Tycho Brahe in 1572. Tycho's careful observations of the supernova helped convince astronomers that the heavens were not immutable and unchanging as Aristotelian philosophy had claimed. Today, the Tycho remnant appears as a beautiful, nearly perfect sphere of shocked gas, expanding at several thousand kilometers per second. Unlike the Crab Nebula, the Tycho remnant resulted from a Type 1a supernova, a different kind of explosion that occurs when a white dwarf in a binary system accumulates too much mass from its companion and explodes completely. Supernova remnants are crucial to the ecology of galaxies. The expanding shock waves heat and compress the interstellar medium, triggering the formation of new stars. The material ejected in the explosion enriches the interstellar medium with heavy elements created during the star's life and in the explosion itself. Elements heavier than iron, including gold, platinum, and uranium, are primarily created in the extreme conditions of supernova explosions and neutron star mergers. Every gold ring, every electronic device containing precious metals, every trace of these elements in our bodies originated in stellar explosions billions of years ago. The shock waves from supernovae also accelerate particles to extremely high energies, creating cosmic rays. These high-energy particles stream through the galaxy at nearly the speed of light. When cosmic rays strike Earth's atmosphere, they create showers of secondary particles that can be detected at the surface. Cosmic rays are a significant component of the radiation environment in space and pose challenges for long-duration space missions and future space exploration. After hundreds of thousands of years, supernova remnants fade and merge with the general interstellar medium. The shock waves slow down and become less distinct. Eventually, all that remains is a slightly enhanced density of gas enriched with heavy elements and perhaps a neutron star or black hole left behind from the original explosion. These remnant stellar cores represent some of the strangest objects in the universe, and they form their own category of galactic graveyards. Let's explore neutron stars, objects so bizarre that they seem more like science fiction than reality. A neutron star is what remains when a massive star's core collapses during a supernova explosion. The collapse is so complete that protons and electrons are forced together to form neutrons, creating an object about 20 kilometers in diameter, but containing more mass than our Sun. To put this in perspective, a neutron star has roughly the mass of the Sun compressed into a sphere the size of a city. A teaspoon of neutron star material would weigh about 1 billion tons, as much as Mount Everest. The physics of neutron stars is extreme. The gravity at the surface of a neutron star is about 200 billion times stronger than Earth's gravity. If you could somehow stand on the surface of a neutron star, which you couldn't because you'd be instantly crushed, you would weigh as much as Mount Everest weighs on Earth. The escape velocity from a neutron star's surface is about 1/3 the speed of light. Light itself is significantly redshifted and bent by the intense gravity as it climbs out of the neutron star's gravitational well. The interior structure of neutron stars is the subject of ongoing research and debate. The outer crust is thought to consist of nuclei embedded in a sea of electrons. As you go deeper, the nuclei become increasingly neutron-rich until you reach a point where neutrons begin to drip out of the nuclei, creating a neutron-rich liquid. Deeper still, you reach the outer core, which is thought to be a superfluid of neutrons with a superconducting component of protons. The inner core is even more mysterious. At such extreme densities, it's possible that quarks, the fundamental particles that make up protons and neutrons, become deconfined, creating exotic states of matter that cannot exist anywhere else in the universe. Many neutron stars are pulsars, rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. If the magnetic axis is misaligned with the rotation axis, the beams sweep through space like lighthouse beams. If Earth happens to lie in the path of the beams, we see regular pulses of radiation, hence the name pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who initially thought the incredibly regular pulses might be a signal from an alien civilization. She jokingly called the source LGM-1 for Little Green Men 1, before it became clear that the pulses had a natural explanation. Pulsars are remarkable natural clocks. The most stable pulsars, called millisecond pulsars, rival atomic clocks in their precision. These pulsars spin hundreds of times per second and lose only microseconds per year in their timing. The stability comes from the enormous rotational energy stored in a rapidly spinning neutron star. A millisecond pulsar contains about as much rotational energy as our Sun will emit over several thousand years. This energy is gradually lost through the emission of electromagnetic radiation and a wind of particles, causing the pulsar to slowly spin down over millions or billions of years. The magnetic fields of neutron stars are the strongest in the universe. A typical neutron star has a magnetic field 1 trillion times stronger than Earth's. Some neutron stars, called magnetars, have fields 1,000 times stronger still, reaching strengths of 10 to the 15th Gauss. These magnetic fields are so strong that they affect the quantum properties of matter. In such intense fields, atoms become elongated into thin rods, and the vacuum itself becomes birefringent, meaning it refracts light differently depending on its polarization. Magnetars occasionally release tremendous bursts of magnetic energy, creating flares that can be detected across the galaxy. Some neutron stars exist in binary systems with companion stars. If the companion is a normal star that evolves and expands, the neutron star can begin to accrete material from its companion. The infalling material forms an accretion disk around the neutron star and releases tremendous amounts of energy as it spirals inward. The material eventually crashes onto the neutron star's surface, releasing a final burst of energy equivalent to thousands of nuclear weapons. These systems are called X-ray binaries because they shine brightly in X-rays produced by the hot accretion disk. In some binary systems, the accretion of material can cause the neutron star to spin faster, transforming it into a millisecond pulsar. These recycled pulsars can spin hundreds of times per second, far faster than pulsars created in supernova explosions. The fastest known pulsar rotates 716 times per second, meaning its equator is moving at about 1/4 the speed of light. At such speeds, the neutron star is nearly at its breakup limit. If it was spinning just a little faster, centrifugal forces would overcome gravity and tear the star apart. When two neutron stars orbit each other, they emit gravitational waves, ripples in space-time predicted by Einstein's general theory of relativity. These gravitational waves carry away energy, causing the orbit to gradually shrink. Eventually, after millions or billions of years, the two neutron stars spiral together and merge in a catastrophic collision. The merger produces a burst of gravitational waves, a bright flash of gamma rays, and a kilonova, a type of optical and infrared transient powered by the radioactive decay of heavy elements synthesized in the merger. The first neutron-star merger detected through gravitational waves occurred in August 2017 and was designated GW170817. The gravitational wave signal lasted about 100 seconds and was detected by both LIGO observatories in the United States and the Virgo Observatory in Italy. About 2 seconds after the gravitational wave signal ended, a short gamma-ray burst was detected by the Fermi and Integral Space Telescopes. Over the following days and weeks, astronomers observed a kilonova that faded from blue to red as the ejected material expanded and cooled. The observations confirmed that neutron star mergers are sites of heavy element synthesis and produce significant quantities of gold, platinum, and other precious metals. Now let's consider the ultimate stellar graveyards, black holes. These objects are so extreme that they represent a breakdown in our normal understanding of space, time, and matter. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from inside a boundary called the event horizon. The name black hole comes from this property. Since light cannot escape, a black hole appears completely black against the background of space. Black holes form when matter is compressed to such extreme density that it overcomes all known forms of pressure that could support it against gravitational collapse. For stellar mass black holes, this happens when the core of a very massive star collapses during a supernova. If the core mass is above a certain threshold, about 3 times the mass of the Sun, even neutron degeneracy pressure cannot halt the collapse, and the core continues to shrink beyond a neutron star, forming a black hole. The physics of black holes is described by Einstein's general theory of relativity, which treats gravity not as a force, but as a curvature of space-time caused by the presence of mass and energy. Near a black hole, space-time is curved so severely that the paths of objects and light are dramatically bent. At the event horizon, space-time curvature becomes infinite, creating a one-way boundary. Anything that crosses the event horizon is inevitably pulled toward the singularity at the center of the black hole, where, according to general relativity, all the black hole's mass is concentrated in a point of infinite density. The singularity is where our current theories break down. The equations of general relativity predict that physical quantities like density and space-time curvature become infinite at the singularity, but infinities in physics usually signal that our theories are incomplete. Most physicists believe that a complete theory of quantum gravity, which would merge quantum mechanics with general relativity, would eliminate the singularity and describe what actually exists at the center of a black hole. Such a theory doesn't yet exist, making the interior of black holes one of the great unsolved mysteries of physics. Despite their name and reputation, black holes are not cosmic vacuum cleaners that suck in everything around them. Far from the event horizon, a black hole's gravity is no different from the gravity of any other object with the same mass. If our Sun were suddenly replaced by a black hole of the same mass, the Earth's orbit wouldn't change at all. We'd freeze and die without sunlight, but we wouldn't be sucked into the black hole. It's only near the event horizon, within a few times the Schwarzschild radius, that the gravity becomes truly extreme and the strange effects of black holes become apparent. One of these strange effects is time dilation. According to general relativity, time runs slower in strong gravitational fields. Near the event horizon of a black hole, this effect becomes extreme. From the perspective of a distant observer, time appears to slow down for anything approaching the event horizon. An object falling toward a black hole would appear to slow down and freeze at the event horizon, never quite crossing it, while light from the object would become increasingly redshifted and dimmed. However, from the perspective of the falling object, nothing special happens at the event horizon. The object crosses it in finite time and continues falling toward the singularity. Another strange effect is spaghettification, the stretching of objects by tidal forces near a black hole. Tidal forces arise because gravity decreases with distance. Near a black hole, the gravitational gradient is so steep that the side of an object closer to the black hole experiences significantly stronger gravity than the far side. For a stellar mass black hole, the tidal forces near the event horizon are strong enough to tear apart any normal object, stretching it into a long, thin shape like spaghetti. Interestingly, for supermassive black holes with millions or billions of solar masses, the event horizon is so far from the singularity that tidal forces at the horizon are relatively weak, and an object could cross the horizon intact. Black holes are difficult to detect directly because they emit no light. However, they can be detected through their effects on nearby matter. If a black hole is part of a binary system with a normal star, it can accrete material from its companion, forming an accretion disk. The infalling material heats up to millions of degrees and emits intense X-rays before crossing the event horizon. These X-ray binaries were the first strong candidates for stellar mass black holes. The prototype is Cygnus X1, an X-ray source associated with a blue supergiant star. The unseen companion has a mass too large to be a neutron star, making it almost certainly a black hole. In 2020, astronomers using the Event Horizon Telescope, a global network of radio telescopes, released the first direct image of a black hole's event horizon. The target was the supermassive black hole at the center of the galaxy M87, which has a mass of about 6.5 billion times the mass of the Sun. The image showed a dark central region, the black hole's shadow, surrounded by a bright ring of emission from the accretion disk. The observations confirmed predictions of general relativity and provided direct visual evidence of the event horizon. In 2022, the Event Horizon Telescope team released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. Despite being much closer than M87's black hole, Sagittarius A star was actually harder to image because material in its accretion disk orbits much faster, causing the image to change significantly over the course of a single night of observations. The team had to develop sophisticated algorithms to reconstruct a stable image from the rapidly varying data. Supermassive black holes, with masses of millions to billions of times the mass of the Sun, reside at the centers of most large galaxies. These giants didn't form from the collapse of individual stars. Instead, they likely grew from smaller seed black holes that formed in the early universe and gradually accumulated mass by accreting gas and merging with other black holes. The relationship between supermassive black holes and their host galaxies is complex and not fully understood, but observations show a strong correlation between black hole mass and the properties of the galactic bulge, suggesting that black holes and galaxies co-evolve. Active galactic nuclei are among the most luminous objects in the universe, powered by supermassive black holes accreting gas at prodigious rates. The accretion disk around an active supermassive black hole can outshine all the stars in the host galaxy combined. Some active galactic nuclei produce powerful jets of material moving at nearly the speed of light, extending for hundreds of thousands or even millions of light years into intergalactic space. These jets are produced by complex interactions between the accretion disk, the black hole's rotation, and powerful magnetic fields, and they're among the most energetic phenomena in the universe. Quasars are the most luminous type of active galactic nuclei. The brightest quasars can be 1,000 times more luminous than the entire Milky Way galaxy, making them visible across billions of light years of space. All the quasars we observe are distant, meaning we're seeing them as they appeared billions of years ago when the universe was young. This tells us that quasars were common in the early universe, but have become rare today. The most likely explanation is that quasars represent a phase in galaxy evolution when supermassive black holes were actively growing. Once the black holes consumed or expelled most of the available gas, they became quiescent, and the quasar phase ended. When two galaxies merge, their central supermassive black holes eventually sink to the center of the merged galaxy and form a binary system. Over millions of years, the binary shrinks through interactions with stars and gas, and eventually the two black holes merge, producing an enormous burst of gravitational waves. The LIGO and Virgo observatories have detected dozens of black hole mergers, though most involve stellar mass black holes rather than supermassive ones. Future space-based gravitational wave detectors like LISA will be sensitive to the mergers of supermassive black holes, opening a new window on galaxy evolution. Black holes also exhibit quantum mechanical properties that lead to surprising predictions. According to Stephen Hawking's calculations, black holes aren't perfectly black, but emit thermal radiation due to quantum effects near the event horizon. This Hawking radiation is incredibly faint for stellar mass or supermassive black holes, with temperatures far below the cosmic microwave background, making it impossible to detect in practice. However, if microscopic black holes exist, they would have high temperatures and radiate away their mass in a spectacular final burst. Hawking radiation leads to the black hole information paradox, a conflict between quantum mechanics and general relativity that remains one of the deepest problems in theoretical physics. Now let's turn our attention to a different kind of galactic graveyard, the remnants not of individual stars but of entire star clusters and dwarf galaxies. The universe is full of ghostly streams and shells of stars that trace out the past tidal disruption and consumption of smaller stellar systems by larger galaxies like the Milky Way. These stellar fossils reveal the violent history of galactic cannibalism and help us understand how large galaxies grow and evolve. The Milky Way is surrounded by a vast halo of ancient stars, star clusters, and stellar streams. Some of these features are the remnants of dwarf galaxies that wandered too close to the Milky Way and were torn apart by tidal forces. As a dwarf galaxy orbits a larger galaxy, the differential gravitational pull stretches it out, pulling stars away from the dwarf's core. Over many orbits, the dwarf galaxy is progressively shredded, leaving behind a stream of stars tracing out its orbital path. One of the best studied examples is the Sagittarius dwarf elliptical galaxy, a small galaxy that is currently being torn apart by the Milky Way. The core of the Sagittarius dwarf is on the far side of the Milky Way from us, about 70,000 light-years away. Stars stripped from the dwarf form streams that wrap completely around the Milky Way, extending across more than 1 million light-years. These streams are visible in maps of stellar positions and velocities obtained by the Gaia Space Telescope, which has measured the positions and motions of over 1 billion stars in the Milky Way. The Magellanic Stream is another dramatic example of tidal disruption. The large and small Magellanic Clouds are dwarf irregular galaxies orbiting the Milky Way. As they orbit, tidal forces and ram pressure from the Milky Way's hot gaseous halo have pulled gas from the Magellanic Clouds, creating a stream that stretches across about 200 degrees of the sky. The stream contains about 1 billion solar masses of neutral hydrogen gas and traces the orbital history of the Magellanic Clouds over the past several billion years. Globular clusters are dense, spherical collections of hundreds of thousands to millions of stars, typically very old and metal-poor. The Milky Way has about 150 known globular clusters, though the actual number is likely higher. Some globular clusters are thought to be the stripped cores of dwarf galaxies that were consumed by the Milky Way. These clusters contain their own smaller-scale graveyards. Stars that form close binaries in the dense cores of globular clusters can evolve into exotic systems including binary pulsars, low-mass X-ray binaries, and cataclysmic variables. The tidal disruption of stars by supermassive black holes creates another type of galactic graveyard. When a star passes too close to a supermassive black hole, tidal forces can overcome the star's self-gravity, tearing it apart. About half the star's material is flung away at high speed, while the rest falls back toward the black hole, forming a temporary accretion disk. The accretion produces a bright flare lasting weeks to months as the stellar debris is consumed. These tidal disruption events provide a way to detect dormant supermassive black holes and study the physics of accretion under extreme conditions. Observations suggest that a few tidal disruption events occur per year in a volume containing 10,000 galaxies. From the perspective of any individual galaxy, these events are rare, occurring perhaps once every 10,000 to 100,000 years. However, in a universe containing hundreds of billions of galaxies, tidal disruption events are occurring constantly somewhere. Wide-field sky surveys designed to detect transient events have discovered dozens of candidate tidal disruption events in recent years, and the rate of discovery is accelerating as survey capabilities improve. Let's consider the fate of white dwarfs, the most common stellar remnants in the galaxy. A white dwarf is not actually white, but can range in color from blue-white when young and hot to red or even black as it cools over billions of years. White dwarfs represent the final fate of all stars, with initial masses below about 8 solar masses, which means more than 95% of all stars will end as white dwarfs. Our Sun will become a white dwarf in about 7 billion years, and the galaxy already contains hundreds of millions or billions of white dwarfs. White dwarfs are supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that arises from the Pauli exclusion principle. This principle states that no two electrons can occupy the same quantum state. In a white dwarf, the electrons are packed so densely that they're forced into high-energy states, creating an outward pressure that balances gravity. The more massive a white dwarf is, the smaller it is, because stronger gravity compresses it more. This inverse relationship between mass and radius continues until you reach the Chandrasekhar limit, about 1.4 solar masses, above which electron degeneracy pressure cannot support the star. A white dwarf contains about the mass of the Sun compressed into a volume about the size of Earth. The density is roughly 1,000,000 times that of water, meaning a teaspoon of white dwarf material would weigh about 5 tons. Despite this extreme density, white dwarfs are not as bizarre as neutron stars or black holes. The gravity at the surface is strong, about 100,000 times Earth's gravity, but not relativistic. Light escaping from a white dwarf is slightly redshifted by gravity, but the effect is measurable rather than dramatic. When a white dwarf first forms, it's extremely hot, with surface temperatures exceeding 100,000 degrees. However, with no internal fusion to provide energy, the white dwarf begins to cool by radiating away its thermal energy. The cooling process is slow because white dwarfs have low surface areas and the degenerate matter has a high heat capacity. A white dwarf takes billions of years to cool from over 100,000 degrees to a few thousand degrees. The coolest white dwarfs in the Milky Way have ages approaching the age of the universe, making them valuable tools for studying galactic history. Some white dwarfs have unusual compositions. Most are made primarily of carbon and oxygen, the products of helium fusion in their progenitor stars. However, stars of very low mass produce white dwarfs made of helium, while more massive progenitors can produce white dwarfs with cores enriched in oxygen, neon, or magnesium. The composition affects the white dwarf's cooling rate and the details of its internal structure, including whether it undergoes crystallization as it cools. Yes, white dwarfs can crystallize. As a white dwarf cools, the carbon and oxygen ions eventually form a solid lattice structure, essentially a giant cosmic diamond. The crystallization releases latent heat, temporarily slowing the white dwarf's cooling. Observations from the Gaia telescope have revealed a pile-up of white dwarfs at certain colors and luminosities, consistent with the expected delay from crystallization. This means the galaxy contains vast numbers of crystallized white dwarfs, essentially diamond stars, slowly fading in the darkness. White dwarfs in binary systems can experience renewed activity through accretion from a companion star. If the companion is a red giant or other evolved star, the white dwarf can pull material from it, forming an accretion disk. The infalling material accumulates on the white dwarf Retria Continue's surface, gradually building up a layer of fresh hydrogen or helium. When this layer reaches sufficient mass and temperature, it ignites in a thermonuclear explosion called a nova. This explosion blows off the accumulated material in a spectacular eruption that can temporarily increase the white dwarf's brightness by a factor of 10,000 to 1,000,000. Unlike supernova, novae don't destroy the white dwarf. After the explosion subsides, the white dwarf continues to accrete material from its companion, and the cycle can repeat. Some systems, called recurrent novae, have been observed to undergo multiple eruptions over human timescales. The most famous example is RS Ophiuchi, which has erupted roughly every 15 to 20 years, with documented outbursts in 1898, 1933, 1958, 1967, 1985, 2006, and 2021. If the accretion rate is steady and the conditions are right, the accumulated material can burn stably on the white dwarf's surface rather than exploding periodically. These systems are called supersoft X-ray sources because they emit most of their energy as soft X-rays from the hot white dwarf surface. Supersoft sources are relatively rare but scientifically important because they represent white dwarfs that are steadily growing in mass, potentially approaching the Chandrasekhar limit. When a white dwarf in a binary system accumulates enough mass to exceed the Chandrasekhar limit, the result is a Type 1a supernova, one of the most important types of cosmic explosions. As the white dwarf approaches the critical mass, the temperature and density in its core reach a point where carbon begins to fuse explosively. Unlike the controlled fusion in a normal star, the degenerate matter of a white dwarf doesn't expand and cool when heated. Instead, the fusion accelerates in a runaway process that takes less than a second to consume the entire white dwarf in a thermonuclear explosion. Type 1a supernovae are remarkably uniform in their properties because they all involve white dwarfs exploding near the same critical mass. This uniformity makes them valuable as standardizable candles for measuring cosmic distances. By comparing the apparent brightness of a Type 1a supernova to its intrinsic luminosity, astronomers can calculate its distance. This technique was used in the late 1990s to discover the accelerating expansion of the universe, a discovery that led to the concept of dark energy and earned the Nobel Prize in Physics in 2011. The explosion of a Type 1a supernova completely destroys the white dwarf, leaving no compact remnant behind. The expanding debris forms a supernova remnant similar to those from core collapse supernova, though with different chemical compositions. Type Ia supernovae are the primary source of iron in the universe. The explosion synthesizes about half a solar mass of radioactive nickel-56, which decays through cobalt-56 to stable iron-56 over the weeks and months following the explosion. This radioactive decay powers the light curve of the supernova, causing it to brighten rapidly, reach peak brightness about 2 weeks after the explosion, and then fade gradually over several months. Not all white dwarfs are isolated or in wide binaries. Some white dwarfs exist in close binary systems with other white dwarfs. These double white dwarf binaries form when both stars in an original binary system evolve and shed their envelopes, leaving behind two white dwarf cores orbiting each other. If the orbital period is short enough, the system emits gravitational waves, which carry away energy and cause the orbit to shrink. Eventually, after millions or billions of years, the two white dwarfs can merge. The outcome of a white dwarf merger depends on the masses involved. If the combined mass exceeds the Chandrasekhar limit, the merger might trigger a type Ia supernova, though this remains debated. If the combined mass is below the limit, the merger produces a single, more massive white dwarf, possibly surrounded by a disk of material. Some unusually massive white dwarfs and some peculiar stars with enhanced helium or carbon abundances may be products of white dwarf mergers. The galaxy also contains hybrid objects that blur the line between different types of stellar remnants. Millisecond pulsars, which we discussed earlier, form when neutron stars accrete material from companion stars and are spun up to rapid rotation rates. Some of these systems transition between different states, sometimes appearing as X-ray binaries when accretion is active, and other times as radio pulsars when accretion ceases. These transitional millisecond pulsars provide valuable insights into the accretion process and the relationship between different types of neutron star systems. Another exotic class of objects is the soft gamma repeaters and anomalous X-ray pulsars, both now understood to be manifestations of magnetars. These objects emit bursts of gamma rays and X-rays that are thought to result from sudden rearrangements of the incredibly strong magnetic fields. The largest flares from magnetars, called giant flares, can briefly outshine the entire X-ray output of the Milky Way. Only 3 giant flares have been observed, in 1979, 1998, and 2004, each releasing as much energy in a fraction of a second as the Sun emits in 1,000 years. Let's now explore the diffuse graveyards, the vast regions of interstellar space filled with the scattered remains of countless dead stars. The interstellar medium, the gas and dust between the stars, is a complex mixture of material with varied origins and properties. A significant fraction of the interstellar medium consists of material ejected by dying stars in the form of planetary nebulae, supernova explosions, and stellar winds. Molecular clouds are the densest and coldest regions of the interstellar medium, with temperatures as low as 10 degrees above absolute zero and densities of thousands to millions of particles per cubic centimeter. Despite these densities being a better vacuum than anything achievable in a laboratory on Earth, they're enormous compared to the typical interstellar density of about 1 particle per cubic centimeter. Molecular clouds are where stars form, making them simultaneously stellar nurseries and graveyards, regions where the material from past stellar generations comes together to form new stars. The dust grains in molecular clouds are themselves stellar graveyards of a sort. These microscopic particles, typically a fraction of a micrometer in size, form in the cool atmospheres of red giant stars and in supernova ejecta. The grains consist of silicates, carbon, and ices containing water, carbon dioxide, ammonia, and methane. Each grain is coated with layers of molecules that have frozen out of the gas phase, creating a complex chemical environment where simple molecules can combine to form more complex ones. Dust grains play a crucial role in the formation of planets and life. The solid material in the protoplanetary disk around a young star consists primarily of dust grains that originated in previous generations of stars. These grains collide and stick together, gradually growing from microscopic sizes to pebbles, boulders, and eventually planetesimals and planets. The rocky planets of our solar system, including Earth, are built from the remnants of ancient stars. The organic molecules present in some dust grains may have been delivered to the young Earth by comets and asteroids, potentially providing raw materials for the origin of life. The most diffuse component of the interstellar medium is the hot ionized medium, which fills much of the volume of the galactic disk. This gas has temperatures of hundreds of thousands or even millions of degrees, and is so tenuous that the density is only about 0.003 particles per cubic centimeter. The hot gas is created and maintained by supernova explosions, which heat vast regions of the interstellar medium to X-ray emitting temperatures. The hot gas is visible in soft X-ray images of the sky, appearing as a diffuse glow pervading the galactic plane. Supernova explosions create superbubbles, enormous cavities in the interstellar medium filled with hot gas. When multiple supernovae explode in the same region over a few million years, as can happen in regions of active star formation, their expanding remnants merge and create a single large bubble that can be hundreds or even thousands of light years across. The most famous example is the Eridanus superbubble, a vast cavity about 1,000 light-years across, centered about 700 light-years from the Sun. This bubble was created by supernovae from the Scorpius-Centaurus Association, a group of young, massive stars. The local bubble is another superbubble that contains our solar system. This cavity, about 300 light-years across, was created by multiple supernovae over the past 10 to 15 million years. The interior of the bubble is filled with hot, tenuous gas at about 1 million degrees, while the walls are defined by denser, cooler clouds of gas and dust. The Sun's location inside the local bubble means that the sky appears darker in the ultraviolet and soft X-ray wavelengths than it would if we were in a denser region of the galaxy. High-velocity clouds are another component of the galactic graveyard, though their origins are diverse and not always related to stellar death. These are clouds of neutral hydrogen gas, moving at velocities that are anomalous compared to simple models of galactic rotation. Some high-velocity clouds are likely material falling into the Milky Way from the intergalactic medium or being pulled from satellite galaxies. Others may be the remnants of old supernova explosions that have blown out of the galactic disk and are now falling back. The Smith cloud is a particularly large example, a cloud of hydrogen with a mass of about 1 million solar masses that is plunging toward the galactic disk at over 200 kilometers per second. The circumgalactic medium, the vast halo of gas surrounding galaxies, is another important repository of stellar material. This gas, with temperatures ranging from thousands to millions of degrees, extends hundreds of thousands of light-years from the galactic center. Much of it was ejected from the galaxy by supernova explosions and stellar winds. The circumgalactic medium is difficult to observe directly because it's so diffuse, but it can be studied through absorption lines in the spectra of distant quasars. These observations reveal that the circumgalactic medium is enriched with heavy elements, confirming that it contains material processed through stars. Galactic fountains and galactic winds transport material from the galactic disk into the halo and beyond. In regions of intense star formation, the combined effects of supernova explosions, stellar winds, and radiation pressure can drive powerful outflows of gas. These outflows can reach velocities of hundreds or thousands of kilometers per second, fast enough to escape the galaxy entirely in some cases. The lost material carries heavy elements into the intergalactic medium, enriching it and seeding future generations of galaxies with the products of stellar nucleosynthesis. The most spectacular examples of galactic winds are found in starburst galaxies, systems undergoing exceptionally intense bursts of star formation. The prototype is M82, a small irregular galaxy about 12 million light-years away. M82 is forming stars at a rate about 10 times higher than the Milky Way, despite being much smaller. The intense star formation drives a powerful galactic wind that can be seen in optical, infrared, X-ray, and radio observations as a bipolar outflow perpendicular to the galactic disk. The wind carries gas out of M82 at about 600 kilometers per second, gradually stripping the galaxy of the raw material needed for future star formation. Intergalactic space itself serves as a vast graveyard for stellar material. The space between galaxies is not empty, but contains a tenuous plasma called the intergalactic medium. In the early universe, this medium consisted almost entirely of hydrogen and helium left over from the Big Bang. However, billions of years of stellar evolution, supernovae, and galactic winds have enriched the intergalactic medium with heavy elements. Current estimates suggest that about half of all the heavy elements ever created by stars now reside in the intergalactic medium rather than in galaxies, having been expelled by galactic winds and other processes. The warm-hot intergalactic medium is a particularly interesting component. This gas, with temperatures between 100,000 and 10 million degrees, is thought to contain a significant fraction of the normal matter in the universe. It's difficult to detect because it's too hot to emit visible light, but too cool to emit strongly in X-rays. However, observations with ultraviolet and X-ray telescopes have revealed absorption lines from highly ionized oxygen and other elements, confirming the existence of this hot, diffuse gas pervading the cosmic web. Galaxy clusters contain huge quantities of hot gas between the galaxies. This intra-cluster medium has temperatures of tens to hundreds of millions of degrees and emits strongly in X-rays. The total mass of hot gas in a cluster can exceed the combined mass of all the stars in all the cluster galaxies. This gas is enriched with heavy elements, showing that it has been processed through stars. The enrichment is not uniform, but shows gradients with higher metallicities near the centers of the brightest cluster galaxies. This suggests that supernova explosions and galactic winds have transported stellar material into the intracluster medium over billions of years. Some of the most beautiful objects in the night sky are the remnants not of stars but of star-forming regions themselves. The Orion Nebula is a spectacular example, a region of active star formation located about 1,400 light-years away. The nebula is illuminated by a group of young, hot stars called the trapezium, which ionize the surrounding gas and cause it to glow. But the Orion Nebula also contains the remains of previous generations of star formation. Infrared observations reveal complex structures including outflows from young stars, shock waves, and dense knots of material. Within the Orion Nebula, we can see protoplanetary disks, or propleids, the raw material from which planets form. These disks are being eroded by the intense radiation from the trapezium stars, creating teardrop-shaped structures with bright bow shocks. The material being eroded away includes dust grains that formed in previous generations of stars, making these regions where past and future stellar generations directly interact. In a few million years, the current generation of stars in the Orion Nebula will have dispersed the remaining gas and dust, leaving behind a young star cluster and, presumably, families of planets. Herbig-Haro objects are another manifestation of stellar youth that involves the recycling of stellar material. These are small patches of nebulosity associated with newly forming stars. They're created when jets of material ejected by young stars collide with the surrounding interstellar medium at speeds of hundreds of kilometers per second. The collisions create shock waves that heat the gas, causing it to glow. Herbig-Haro objects are transient phenomena that appear and evolve over decades, providing a unique opportunity to watch stellar processes in real time. Now let's consider the fate of the universe itself and what the ultimate galactic graveyard might look like. The far future of the universe depends on several factors, including the nature of dark energy, the total amount of matter in the universe, and the stability of protons. Current observations suggest that the universe will continue to expand forever, with the expansion accelerating due to dark energy. This leads to a scenario sometimes called the heat death of the universe, where the cosmos gradually becomes colder, darker, and more diffuse over trillions of years. In the near term, by which I mean the next few 100 billion years, star formation will gradually decline as galaxies consume their available gas. Star formation has already declined significantly from its peak about 10 billion years ago. As star formation ceases, the mix of stars in galaxies will change. Short-lived massive stars will quickly die out, leaving only lower-mass stars. After about 1 trillion years, all star formation will have ceased, and the longest-lived stars, red dwarfs with masses around 1/10 of the Sun's mass, will begin to die. The era of stellar death will last for tens of trillions of years as the last stars exhaust their fuel and fade away. By about 100 trillion years from now, the last stars will have died, and the universe will enter what's called the degenerate era. Galaxies will consist entirely of stellar remnants, white dwarfs, neutron stars, and black holes, along with the failed stars known as brown dwarfs and the planets that survived the deaths of their parent stars. These galaxies will emit only faint infrared and microwave radiation from the cooling remnants. During the degenerate era, stellar remnants will occasionally collide in the dense cores of galaxies, producing brief flares of light. White dwarf collisions might produce dim supernovae, while collisions involving neutron stars or black holes could produce gravitational wave bursts and high-energy transients. These rare events will be the only significant energy releases in an otherwise dark and cold universe. Over time, even these collisions will become less frequent as dynamical interactions eject most stellar remnants from galaxies into the expanding intergalactic space. The gravitational interactions that eject stars from galaxies also cause the remaining stars to gradually spiral inward. Over timescales of about 10 to the 20th years, about 100 billion years, most of the stellar remnants in a galaxy will either be ejected into intergalactic space or spiral into the central supermassive black hole. The black hole will grow as it consumes stellar remnants, but most of the galaxy's mass will be dispersed. What remains will be isolated stellar remnants drifting through an ever-expanding void, moving apart from each other as the universe expands. If protons are stable, as current evidence suggests but doesn't conclusively prove, then white dwarfs, neutron stars, and the planets and asteroids made of normal matter will persist essentially forever, though they'll cool to nearly absolute zero. However, some theories predict that protons have a finite but extremely long lifetime, perhaps 10 to the 35 years or longer. If protons do decay, then over immense timescales all normal matter will gradually disintegrate into lighter particles and radiation. Neutron stars would be the first to go, as they consist of the densest concentration of protons and neutrons. White dwarfs and planets would follow over even longer timescales. In the far future, even black holes won't be permanent. Hawking radiation causes black holes to very slowly evaporate, losing mass and shrinking over time. A black hole with the mass of the Sun would take about 10 to the 67 years to evaporate, an incomprehensibly long time. More massive black holes take even longer. The supermassive black holes at the centers of galaxies, with masses of millions to billions of solar masses, would take up to 10 to the 100 years to evaporate. This is so long that the number can't meaningfully be comprehended. It's a 1 followed by 100 zeros, far longer than the current age of the universe, which is less than 10 to the 10th years. The final evaporation of a black hole is a spectacular event, at least in relative terms. As the black hole shrinks, its temperature increases inversely with its mass. A black hole approaching the end of its life becomes extremely hot and radiates intensely. In its final second, a solar mass black hole releases about 10 to the 30 ergs of energy, equivalent to the Sun's total energy output over about 3 years, all in a brief final flash. After the black hole evaporates completely, all that remains is the thermal radiation it emitted, photons traveling outward into the ever-expanding universe. The ultimate fate of the universe in this scenario is a dark, cold, diffuse sea of photons, neutrinos, and possibly other stable particles, all at temperatures infinitesimally close to absolute zero. The universe will have reached maximum entropy, a state where no further change or energy extraction is possible. This is the heat death of the universe, the ultimate and final galactic graveyard. All the stars that ever shone, all the black holes that ever formed, all the galaxies that ever existed will have decayed away, leaving only a faint whisper of radiation in an infinite void. However, our understanding of the far future comes with significant uncertainties. Dark energy, which drives the accelerating expansion of the universe, is poorly understood. If dark energy strengthens over time, it could lead to a Big Rip scenario, where the accelerating expansion eventually becomes so strong that it tears apart galaxies, stars, planets, and eventually even atoms and subatomic particles. If dark energy weakens or reverses, the universe could eventually stop expanding and recollapse in a big crunch, ending in a singularity similar to the Big Bang but in reverse. There are also speculative possibilities involving quantum effects or unknown physics. Some theories suggest that the vacuum of space might be metastable and could decay to a lower energy state, with the transition propagating through the universe at the speed of light. This vacuum decay would fundamentally alter the laws of physics in the affected region, destroying everything in its path. There's no evidence this will happen, but if the current vacuum is indeed metastable, the decay could occur at any time, though the probability is likely extremely small. Despite these possibilities for ultimate doom, let's return to the present and near future, where galactic graveyards continue to tell us stories about the universe's history and structure. One of the most exciting recent developments has been the use of gravitational wave astronomy to study stellar remnants. The detection of gravitational waves from merging black holes and neutron stars has opened an entirely new window on the universe, allowing us to observe phenomena that emit little or no electromagnetic radiation. The first gravitational wave detection, announced in February 2016, came from the merger of two black holes with masses about 30 times that of the Sun. This event, which occurred about 1.3 billion years ago, released more power in gravitational waves than all the stars in the observable universe combined emit as light. The detection confirmed a key prediction of general relativity and demonstrated that stellar mass black holes more massive than about 20 solar masses exist, which was previously uncertain. Since that first detection, the LIGO and Virgo observatories have detected dozens of black hole mergers, along with several neutron star mergers and possible black hole neutron star mergers. Each detection provides information about the masses, spins, and orbital parameters of the merging objects. Statistical analysis of the population of detections is revealing how black holes and neutron stars form, how they pair up in binary systems, and how their properties depend on the metallicity and other properties of their progenitor stars. The gravitational wave detections have also revealed that black hole mergers can form more massive black holes than previously thought possible from single star evolution. Some of the detected mergers have produced black holes with masses exceeding 80 solar masses. These could be the products of hierarchical mergers, where black holes that formed from earlier mergers merge again with other black holes. This process could build up the intermediate mass black holes that bridge the gap between stellar mass and supermassive black holes, potentially explaining how supermassive black holes formed so early in the universe's history. Multi-messenger astronomy, the coordinated observation of cosmic events using both gravitational waves and electromagnetic radiation, is providing unprecedented insights into neutron star mergers. The first multi-messenger observation, GW170817, was detected by gravitational wave observatories and followed up by telescopes across the electromagnetic spectrum. The observations confirmed that neutron star mergers produce short gamma-ray bursts and kilonovae, and they provided the first direct evidence that these mergers are major sites of our process nucleosynthesis, the rapid neutron capture process that produces about half the elements heavier than iron. The kilonova associated with GW170817 faded from blue to red over several days as the ejected material expanded and cooled. Spectroscopic observations revealed signatures of heavy elements including lanthanides and actinides. Based on the observed brightness and color evolution, astronomers estimated that the merger produced several Earth masses of gold and platinum, along with substantial quantities of other heavy elements. This single event likely produced more gold than exists in the entire Earth, all created in a few seconds of extreme physics. Looking forward, next-generation gravitational wave detectors will dramatically expand our ability to study stellar remnants. The Einstein telescope, a proposed European gravitational wave observatory, would be about 10 times more sensitive than current detectors and could observe black hole and neutron star mergers throughout the observable universe. The Cosmic Explorer, a proposed US detector with 40-kilometer arms, would have similar capabilities. These detectors would see thousands or tens of thousands of mergers per year, providing detailed statistics on the populations of stellar remnants and their properties. Space-based gravitational wave detectors will open access to lower frequencies inaccessible from the ground. The Laser Interferometer Space Antenna, or LISA, planned for launch in the 2030s, will observe gravitational waves from merging supermassive black holes. Extreme mass ratio inspirals, where stellar mass objects spiral into supermassive black holes and close white dwarf binaries in our own galaxy. LISA will provide a census of the population of double white dwarf binaries in the Milky Way and measure the merger rate of supermassive black holes across cosmic history. Another frontier in studying galactic graveyards is the search for stellar mass black holes that are not in binary systems and don't have accretion disks. These isolated black holes are essentially invisible, but they can be detected through gravitational microlensing. When a black hole passes between Earth and a background star, The black hole's gravity bends the light from the star, causing the star to appear to brighten temporarily. The duration and shape of the brightening event depend on the mass of the lensing object and its distance. Several candidate isolated black holes have been detected through this method, and future microlensing surveys should detect many more. The study of supernova remnants continues to yield surprises and insights. High-resolution X-ray and radio observations reveal complex structures including shells, jets, bullets of fast-moving material, and evidence for particle acceleration to extremely high energies. Some supernova remnants show strong asymmetries, suggesting that the original explosion was not spherically symmetric. Three-dimensional computer simulations of core collapse supernovae reveal that the explosions are indeed highly asymmetric due to turbulence and instabilities in the region between the protoneutron star and the shockwave. Recent observations have discovered some unusual supernova remnants that don't fit neatly into previous categories. The remnant PR30, for instance, appears to be an inverted type Ia supernova remnant where the ejecta are moving inward rather than outward. This bizarre structure likely results from the interaction of the supernova with material ejected by the progenitor system before the explosion. Other remnants show evidence for multiple explosions or unusual progenitor systems, revealing that stellar death can be more complex and varied than simple models suggest. The search for the progenitor stars of supernovae has become an active area of research. When a supernova is discovered, astronomers search archival images of the host galaxy to see if the progenitor star was bright enough to have been detected before the explosion. These pre-explosion detections or non-detections provide crucial constraints on the progenitor's mass, luminosity, and evolutionary state. Surprisingly, many core collapse supernovae have progenitors that are fainter than expected, suggesting that massive stars often lose more mass through winds and eruptions than theoretical models predict. Superluminous supernovae are an extreme class of explosions that are 10 to 100 times brighter than normal supernovae. The power source for these events is debated. Some may be powered by the spin-down of rapidly rotating, highly magnetized neutron stars called magnetars. The rotational energy of a newly formed magnetar is enormous, comparable to the kinetic energy of a supernova explosion. If this energy can be efficiently transferred to the expanding ejecta, it could power a superluminous supernova. Other models invoke pair instability supernova, which occur in extremely massive stars where photons in the core are so energetic they spontaneously convert into electron-positron pairs, causing a catastrophic loss of pressure support. Pair instability supernovae are thought to be the deaths of stars with initial masses between about 130 and 260 solar masses. These stars are so massive and luminous that they were probably rare even in the early universe when the first stars formed from pristine hydrogen and helium. A pair instability supernova completely destroys the star, leaving no remnant behind. The explosion produces large quantities of radioactive nickel-56, up to tens of solar masses, making these events extremely bright. The light curve, powered by nickel decay, remains bright for many months, much longer than typical supernovae. The quest to understand the first stars, called Population 3 stars, is intimately connected with understanding their deaths and remnants. The first stars formed about 100 to 200 million years after the Big Bang, from gas containing only hydrogen, helium, and trace amounts of lithium. Without heavy elements to facilitate cooling, the star-forming gas could not fragment as efficiently as in later generations, leading to the formation of very massive stars, possibly hundreds of solar masses. These massive stars lived fast and died young, exploding as supernovae or collapsing directly to black holes after only a few million years. The deaths of the first stars were crucial to cosmic evolution. Their supernova explosions enriched the pristine gas with heavy elements, allowing subsequent generations of stars to form more efficiently and reach lower masses. The black holes left behind by the most massive first stars may have served as seeds for the supermassive black holes that grew at the centers of galaxies. Some theorists have even suggested that the most massive first stars could have collapsed to form intermediate mass black holes of hundreds or thousands of solar masses, which then merged to form the supermassive black holes observed at high redshift. Observations with the James Webb Space Telescope are revealing galaxies as they appeared less than 500 million years after the Big Bang, bringing us closer to the era of the first stars. While we haven't yet directly detected population 3 stars, we're observing galaxies from an era when such stars may have still been forming. These early galaxies show evidence for intense star formation and chemical enrichment, consistent with early generations of massive stars living and dying rapidly. Future observations may detect the signature of population 3 stars in these early galaxies, or even catch the explosions of individual first stars. Let's now explore some of the strangest and most exotic objects in galactic graveyards. Thorne-Jitkow objects are hypothetical hybrid stars consisting of a neutron star embedded in the core of a red giant or supergiant star. These bizarre objects could form if a neutron star in a binary system spirals into its companion and settles into the companion's core. The neutron star would accrete material and release energy through accretion and possibly through unusual nuclear reactions at the neutron star's surface. Thorne-Jitkow objects would appear as unusually cool but overluminous red giants with distinctive chemical abundances. A few candidates have been proposed, but none are yet confirmed. Quark stars are another speculative type of object. In the cores of the most massive neutron stars, the pressure and density might be high enough to overcome the strong force binding quarks into protons and neutrons. The quarks would become deconfined, creating a state of matter called quark matter or strange matter. A star made primarily of quark matter would be similar to a neutron star but slightly smaller and denser. Some observations of unusually small or rapidly rotating neutron stars have been interpreted as possible evidence for quark stars, but the existence of these objects remains uncertain. Strange stars or strangelets are related, but even more exotic. If strange quark matter is more stable than normal matter, it might be truly stable, meaning a strange star would represent the actual ground state of matter, rather than being supported against collapse by degeneracy pressure. Strange stars would have bizarre properties including extraordinarily high densities and the potential to convert normal matter into strange matter on contact. There's no confirmed evidence for strange stars, and many physicists doubt they exist, but they remain an interesting theoretical possibility. Primordial black holes are a different class of exotic object. Unlike stellar black holes that form from collapsing stars, primordial black holes could have formed in the very early universe from density fluctuations or phase transitions. These black holes could have a wide range of masses, from microscopic to thousands of solar masses or more. Small primordial black holes with masses less than about 10 to the 12th kilograms would have evaporated by now through Hawking radiation. More massive ones could still exist and might account for some of the universe's dark matter. The possible role of primordial black holes in dark matter is controversial. Recent observations, including gravitational wave detections of black hole mergers and microlensing surveys, place strong constraints on the fraction of dark matter that could consist of primordial black holes. Current data suggest that primordial black holes cannot account for all dark matter, but they might make up a small fraction. If primordial black holes with masses of tens of solar masses exist, they could be hiding in plain sight, masquerading as stellar mass black holes formed from massive stars. Neutron star white dwarf binaries are another fascinating class of objects. These systems form when a massive star in a binary system explodes as a supernova, leaving behind a neutron star, and the less massive companion later evolves to form a white dwarf. The neutron star often manifests as a radio pulsar, and the precise timing of pulsar pulses allows astronomers to measure the orbital parameters with extraordinary precision. These measurements provide tests of general relativity and allow the masses of both stars to be determined with higher accuracy than almost any other stellar mass measurements. The Hulse-Taylor binary pulsar, discovered in 1974, was the first binary pulsar discovered and remains one of the most important. The system consists of a pulsar and another neutron star orbiting each other with a period of about 8 hours. Careful timing of the pulsar showed that the orbit is shrinking at exactly the rate predicted by general relativity through the emission of gravitational waves. This indirect detection of gravitational waves earned Russell Hulse and Joseph Taylor the Nobel Prize in Physics in 1993, more than 20 years before gravitational waves were directly detected by LIGO. Double pulsar systems, where both neutron stars are observed as pulsars, are exceptionally rare and valuable. Only one is currently known, PSR J0737-3039, discovered in 2003. In this system, we can see pulses from both neutron stars, providing redundant measurements and additional tests of general relativity. The system has confirmed relativistic effects including orbital decay, gravitational redshift, and Shapiro delay, the time delay of pulses as they pass through the curved spacetime near the companion. All measurements agree with general relativity to within the observational uncertainties, providing the most stringent tests of the theory in strong field conditions. Spider pulsars are a class of millisecond pulsars with low-mass companions that are being evaporated by the pulsar's intense radiation and particle wind. These systems are divided into black widows, where the companion has less than about 0.05 solar masses, and redbacks, where the companion is slightly more massive, between 0.1 and 0.5 solar masses. The companions are often bloated and distorted by heating from the pulsar, and in some cases the companion is being completely evaporated with material streaming away into space. These systems represent an extreme form of stellar cannibalism, where the pulsar is slowly destroying its companion. Recycled pulsars in globular clusters provide insights into stellar dynamics and binary evolution in dense stellar environments. Globular clusters contain hundreds of thousands to millions of old stars packed into a small volume, leading to frequent close encounters and collisions. These interactions can form and modify binary systems, including systems where a neutron star accretes material from a companion and is spun up to become a millisecond pulsar. Some globular clusters contain dozens of millisecond pulsars, far more than would be expected in a similarly sized region of the galactic disk. Blue stragglers are another product of stellar interactions in dense environments. These stars appear younger and bluer than other stars in a cluster, lying on the main sequence above the cluster's turn-off point. Blue stragglers form through mass transfer in binary systems or through stellar collisions and mergers. They represent a form of stellar rejuvenation where a star gains new hydrogen fuel and extends its life. When these stars eventually die, they will continue leave behind remnants that are more massive than typical for their cluster's age, creating anomalous stellar graveyards. The cores of globular clusters are particularly interesting as stellar graveyards. Dynamical interactions over billions of years cause massive objects, including stellar remnants, to sink toward the cluster center through a process called mass segregation. The cores of some clusters likely contain substantial populations of white dwarfs, neutron stars, and possibly stellar mass black holes, though the black holes may be ejected through strong gravitational interactions. Recent observations suggest that some globular clusters may harbor intermediate mass black holes in their cores, with masses of hundreds to thousands of solar masses. Intermediate mass black holes represent a largely unexplored population that bridges the gap between stellar mass and supermassive black holes. Their existence has been predicted by theory, but confirming examples remain elusive. The best candidates include ultraluminous X-ray sources, which are point sources in nearby galaxies that emit more X-rays than expected from stellar mass black holes, and the possible massive objects at the centers of some globular clusters and dwarf galaxies. If intermediate mass black holes exist in large numbers, they would represent an important but hidden component of galactic graveyards. Hypervelocity stars are another exotic phenomenon related to stellar death and galactic dynamics. These are stars moving fast enough to escape the Milky Way's gravity, with velocities exceeding 500 kilometers per second. Several formation mechanisms have been proposed. Some hypervelocity stars may be ejected when their binary companions are tidally disrupted by the supermassive black hole at the galactic center, giving the surviving star a gravitational slingshot. Others may be ejected through three-body or four-body interactions in dense star clusters, or through supernova explosions in binary systems, where the kick from the asymmetric explosion unbinds the system and sends both stars flying apart at high speeds. The study of hypervelocity stars provides insights into binary star evolution, supernova physics, and the mass distribution of the galaxy. By tracing back the trajectories of hypervelocity stars, astronomers can identify their points of origin and learn about the environments that produced them. Some hypervelocity stars appear to come from the galactic center, supporting the idea that interactions with the supermassive black hole play a role. Others come from the disk or halo, suggesting multiple formation mechanisms. Runaway stars are somewhat slower than hypervelocity stars, but still moving unusually fast, with velocities of tens to hundreds of kilometers per second, relative to the average stellar motion. Many runaway stars are massive stars that were ejected from star clusters or binary systems. Some show bow shocks in infrared images, structures formed where the star's wind collides with the surrounding interstellar medium. These bow shocks reveal the direction and speed of the star's motion through space. When runaway stars eventually die as supernovae, they create supernova remnants in locations far from any obvious star-forming region, creating isolated pockets of stellar graveyard material. Let's turn our attention to the observational techniques used to study galactic graveyards. Multi-wavelength astronomy is essential because different components of stellar remnants emit radiation at different wavelengths. Hot gas emits X-rays, warm gas emits optical and ultraviolet light, cold gas and dust emit infrared and radio waves, and the hottest electrons produce radiosynchrotron emission. By observing across the electromagnetic spectrum, astronomers can map the complete structure and physical conditions in supernova remnants, planetary nebulae, and other objects. X-ray observations are particularly important for studying high-energy phenomena in galactic graveyards. Space telescopes like Chandra, XMM Newton, and NuSTAR observe X-rays from hot gas in supernova remnants, accretion disks around compact objects, and the surfaces of neutron stars. X-ray spectra reveal the temperature, density, and chemical composition of the emitting gas. In supernova remnants, X-ray observations can distinguish between emission from the shocked interstellar medium and emission from the supernova ejecta, which have different chemical compositions. Radio observations trace synchrotron emission from relativistic electrons spiraling in magnetic fields. This emission is particularly strong in supernova remnants, where shock waves accelerate particles to high energies, and in the nebulae powered by pulsar winds like the Crab Nebula. Radio observations can also detect pulsars directly through their pulsed emission, and radio interferometry can map the magnetic field structure in supernova remnants through observations of polarized emission. Infrared observations penetrate dust that obscures optical light, revealing embedded protostars in molecular clouds and the cool dust in planetary nebulae and supernova remnants. The Spitzer Space Telescope and now the James Webb Space Telescope have revolutionized infrared astronomy, providing unprecedented views of dusty environments. Infrared spectroscopy can identify specific molecules and dust grain compositions, tracing the chemical evolution of material from stellar interiors to the interstellar medium. Optical observations provide beautiful images and detailed spectra of planetary nebulae, supernova remnants, and other galactic graveyard objects. Spectra reveal the velocities of gas through Doppler shifts, the physical conditions through line ratios, and the chemical abundances through the strengths of emission lines from different elements. High-resolution spectroscopy can resolve individual shells and knots within nebulae, revealing their three-dimensional structure and kinematics. Ultraviolet observations access emission from hot gas and highly ionized atoms. The Hubble Space Telescope's ultraviolet capabilities have been used to study hot white dwarfs, shocked gas in supernova remnants, and the hot winds from massive stars that will eventually die as supernovae. Ultraviolet absorption line spectroscopy can detect thin, hot gas that doesn't emit strongly at other wavelengths, revealing components of supernova remnants and the circumgalactic medium that are invisible in other wavebands. Gamma-ray observations detect the highest energy photons produced by the most extreme physical processes. The Fermi Gamma Ray Space Telescope has detected gamma-ray emission from supernova remnants, confirming that these objects accelerate particles to extremely high energies and act as cosmic ray sources. Some pulsars emit most of their energy as gamma rays, and gamma-ray observations have discovered many pulsars that are weak or undetectable at radio wavelengths. Gamma-ray bursts, the most luminous explosions in the universe, are detected by dedicated satellite missions and provide insights into the depths of the most massive stars and the formation of black holes. Neutrino astronomy offers a unique window on stellar death because neutrinos interact so weakly with matter that they stream freely from the cores of collapsing stars. The only direct detection of neutrinos from a supernova came from SN 1987A, a supernova that exploded in the Large Magellanic Cloud. About 20 neutrinos were detected by underground detectors on Earth, arriving about 3 hours before the light from the explosion. These neutrinos came directly from the proto-neutron star at the moment of core collapse, providing unique information about the conditions in the stellar core. Future supernova neutrino detections will provide much more detailed information, potentially revealing the formation of a neutron star or black hole in real time. Gravitational wave astronomy, as we've discussed, has opened an entirely new window on compact object mergers. But gravitational waves could potentially reveal other phenomena in galactic graveyards as well. Asymmetric supernova explosions should produce bursts of gravitational waves, though current detectors are not sensitive enough to detect these bursts except from very nearby supernovae. Rapidly rotating neutron stars that are not perfectly symmetric could emit continuous gravitational waves, and searches for these signals are ongoing. The stochastic background of gravitational waves from all the black hole and neutron star mergers throughout the universe's history may be detectable with improved sensitivity. Time domain astronomy, the systematic search for objects that change in brightness over time, is revealing previously hidden components of galactic graveyards. Wide-field surveys like the Zwicky Transient Facility, the Asteroid Terrestrial Impact Last Alert System, and the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time will discover thousands of supernovae, novae, tidal disruption events, and other transients each year. The large samples will allow statistical studies of rare events and reveal the diversity of stellar death processes. Computational modeling is essential for interpreting observations of galactic graveyards. Modern supercomputers can simulate the collapse of stellar cores, the explosion of supernovae, the formation and evolution of supernova remnants, and the mergers of compact objects. These simulations require sophisticated physics, including nuclear reactions, neutrino transport, magnetic fields, and general relativity. By comparing simulations with observations, astronomers can test their understanding of the underlying physics and refine their models. Three-dimensional simulations of core collapse supernovae have revealed that the explosions are inherently three-dimensional and chaotic, driven by turbulence and instabilities. This explains why supernova remnants are often asymmetric and why neutron stars receive kicks that send them moving rapidly through the galaxy. The simulations also help explain why some massive stars may fail to explode as supernovae and instead collapse directly to black holes, a process that may have occurred in the mysterious transient N6946 BH1, where a massive star disappeared without producing a bright supernova. Chemical evolution models track how the abundances of different elements change over cosmic time as successive generations of stars form, live, and die. These models take into account star formation rates, the initial mass function that determines how many stars of each mass form, stellar yields that specify how much of each element is produced and returned to the interstellar medium, and mixing processes that distribute the material. By comparing model predictions with observed abundances in stars of different ages and in the interstellar and intergalactic media, astronomers can reconstruct the history of element production and understand how galactic graveyards have shaped cosmic chemistry. Nuclear synthesis calculations determine which elements are produced in different stellar environments and processes. Hydrogen and helium, along with traces of lithium, were produced in the Big Bang. Carbon, nitrogen, oxygen, and some heavier elements up to iron are produced by fusion in stellar interiors and ejected in planetary nebulae and supernova explosions. Elements from iron to around germanium are produced primarily in Type 1a supernovae. Elements heavier than iron are produced mainly by neutron capture processes, the slow process in asymptotic giant branch stars and the rapid process in neutron star mergers, and possibly in some supernovae. The most recent advances in our understanding of nucleosynthesis have come from multi-messenger observations of neutron star mergers. The detection of GW170817 and its associated kilonova confirmed theoretical predictions that the rapid neutron capture process occurs in these mergers and produces substantial quantities of heavy elements. Detailed modeling of the kilonova light curve and spectra has provided estimates of the yields of different elements, showing that neutron star mergers can explain the observed cosmic abundances of many heavy elements, including gold, platinum, uranium, and the rare earth elements. Archaeological connections between Earth and galactic graveyards provide a tangible link to stellar death. The elements that make up our planet and our bodies were forged in stellar furnaces and stellar explosions. The iron in your blood was created in a massive star and ejected when that star exploded as a supernova billions of years ago. The gold in any jewelry you wear was likely created in a neutron star merger. The calcium in your bones, the oxygen you breathe, the carbon in your cells, all have cycled through multiple generations of stars over the 13.8 billion year history of the universe. Some isotopes on Earth carry specific signatures of their stellar origins. Radioactive isotopes like aluminum-26, iron-60, and plutonium-244 have half-lives short enough that any primordial amounts should have decayed away long ago. Yet these isotopes are found in meteorites and deep-sea sediments, indicating that they were injected into the solar system by nearby stellar explosions. The discovery of iron-60 in deep-sea crusts and lunar samples suggests that a supernova exploded within a few hundred light-years of Earth about 2 to 3 million years ago, possibly affecting Earth's climate and biosphere. The concept of cosmic recycling emphasizes that galactic graveyards are not endpoints but waypoints in an ongoing cycle. Material ejected by dying stars mixes with the interstellar medium and is incorporated into new generations of stars and planets. Each cycle enriches the mix with heavier elements, progressively increasing the metallicity of the gas from which stars form. Our Sun is a third-generation star, formed from material enriched by at least 2 previous generations of stellar birth and death. Future generations of stars will form from material enriched by our Sun and its contemporaries. This cosmic recycling has profound implications for the possibility of life elsewhere in the universe. Life as we know it requires elements like carbon, nitrogen, oxygen, phosphorus, and sulfur, along with trace amounts of many heavier elements. These elements didn't exist when the universe began. They were created by stars. The first generation of stars contained only hydrogen and helium, making it impossible for planets like Earth to form. Only after these first stars died and enriched the interstellar medium with heavier elements could rocky planets and the chemistry necessary for life emerge. The timeline of cosmic chemical enrichment thus sets a lower bound on when life could have emerged in the universe. The first potentially habitable planets likely formed about 10 billion years ago, when the universe was about 4 billion years old and had been enriched sufficiently with heavy elements. This means life on Earth is not necessarily among the earliest life in the universe, and there could be civilizations billions of years more advanced than ours. Conversely, if life is extremely rare or difficult to start, Earth's life could be among the first or even the first in the observable universe. Galactic habitable zones represent regions of galaxies where conditions are most favorable for the development of complex life. The inner regions of galaxies have high rates of star formation and supernova explosions, which could sterilize planets with frequent bursts of radiation. The outer regions have low metallicities, making it difficult to form rocky planets with sufficient heavy elements for life. The galactic habitable zone lies in between, where metallicity is sufficient but supernova rates are not too high. Our Sun lies within the Milky Way's habitable zone, though the concept remains debated. The role of supernovae in extinctions on Earth is a subject of ongoing research. A nearby supernova, within about 30 light-years, could damage Earth's ozone layer with gamma rays and cosmic rays, potentially causing a mass extinction. The late Devonian extinction, about 375 million years ago, has been tentatively linked to a supernova based on plant spore evidence suggesting UV damage. Similarly, the Pliocene-Pleistocene boundary extinctions around 2 to 3 million years ago roughly coincide with the timing of the nearby supernova indicated by iron-60 deposits. However, the effects of nearby supernovae on Earth's biosphere are uncertain. While a very nearby supernova within 10 light-years would certainly be catastrophic, the effects of more distant supernova depend on many factors, including the supernova type, the geometry of the explosion, and the state of Earth's magnetic field and atmosphere. Most estimates suggest that supernovae within about 30 light-years are required to cause significant damage, and such events are rare, occurring perhaps once every few hundred million years in any given location. Looking to the future, humanity's expansion into space will bring us into more direct contact with galactic graveyards. Space travelers will need to navigate through regions filled with the remnants of dead stars, cosmic rays accelerated by supernova shocks, and the intense radiation environments around neutron stars and black holes. Understanding these hazards is essential for long-duration space missions and eventual interstellar travel. Cosmic rays pose a significant challenge for space exploration. These high-energy particles, accelerated primarily by supernova remnants, pervade the galaxy. They can damage electronics, increase cancer risk for astronauts, and even affect the climate of planets through their interactions with atmospheres. Shielding against cosmic rays is difficult because the most energetic particles penetrate substantial amounts of material. Future spacecraft may need advanced shielding technologies, possibly including active magnetic shielding that mimics Earth's protective magnetosphere. The possibility of harvesting resources from stellar remnants is an intriguing concept for far future civilizations. White dwarfs contain vast quantities of carbon and oxygen in the form of a giant crystal, essentially an enormous diamond. Neutron stars contain exotic states of matter that might have valuable properties if they could somehow be extracted and stabilized. Black holes could potentially serve as energy sources through the Penrose process or by dropping matter into the accretion disk and capturing the emitted radiation. These ideas remain firmly in the realm of speculation, but they illustrate how galactic graveyards might be valuable rather than just dangerous. Communicating with extraterrestrial civilizations, if they exist, might involve using pulsars as beacons or reference points. Pulsars have precise, stable periods that can serve as natural clocks. The Pioneer plaques and Voyager golden records carried by spacecraft leaving the solar system include maps showing Earth's location relative to 14 pulsars. An advanced civilization receiving these artifacts could use the pulsar periods to determine when the spacecraft were launched and potentially when human civilization existed, even if they're not found for millions of years, and the pulsar's periods have changed measurably. Pulsars have also been proposed as navigational beacons for interstellar travel. A spacecraft equipped with an X-ray telescope could observe multiple pulsars and use their precise timing to determine its position and velocity anywhere in the galaxy, creating a sort of cosmic GPS system. This technology, called X-ray pulsar navigation or XNAV, is being developed and tested on spacecraft in Earth orbit. It could eventually enable autonomous navigation for deep space missions without needing to communicate with Earth. The scientific study of galactic graveyards continues to accelerate with new observatories and techniques. The upcoming Nancy Grace Roman Space Telescope will conduct wide-field infrared surveys that will discover thousands of supernovae and other transients. The Square Kilometre Array, a radio telescope under construction, will be 50 times more sensitive than any existing radio telescope and will discover and time pulsars throughout the galaxy and beyond. The extremely large telescope, with a 39-meter mirror, will be able to study supernova remnants and planetary nebulae in distant galaxies with unprecedented detail. Amateur astronomers and citizen scientists play important roles in studying galactic graveyards. Supernovae in nearby galaxies are often first discovered by dedicated amateur astronomers who scan the sky regularly. Citizen science projects allow volunteers to classify galaxy images, search for planetary nebulae, or help identify interesting transient events in large datasets. The distributed computing project Einstein at Home uses volunteers' spare computer time to search for pulsars and gravitational wave signals in data from observatories around the world. Educational outreach using galactic graveyards captures public imagination and inspires the next generation of scientists. The stunning images of planetary nebulae and supernova remnants from Hubble and other telescopes are among the most popular and widely distributed astronomy images. The detection of gravitational waves from merging black holes made headlines around the world. The discovery that gold and platinum come from neutron star mergers connects cosmic violence to everyday objects in a way that people find fascinating and memorable. Philosophical and existential questions arise from our study of galactic graveyards. The realization that we are made of stardust, literally composed of atoms forged in stellar furnaces billions of years ago, provides a profound connection between humanity and the cosmos. The vast scales of time and space involved in cosmic recycling put human concerns in perspective, while also highlighting how we are integral parts of cosmic evolution. We are a way for the universe to know itself, as Carl Sagan famously said, made possible by the deaths of countless stars over billions of years. The impermanence of stars and galaxies reflects the universal principle that all things change. Stars are born, live, and die. Galaxies merge and evolve. Even black holes eventually evaporate. This cosmic impermanence parallels the impermanence we experience in our own lives and has been noted by philosophers and contemplatives across cultures. Yet the material continuity through recycling shows that endings are also beginnings, and death enables new forms of existence. The anthropic principle, the observation that the universe's properties are compatible with our existence as observers, life takes on special meaning in the context of galactic graveyards. If stars couldn't form, or if they couldn't die and enrich the interstellar medium with heavy elements, we wouldn't exist to wonder about the universe. The fact that we exist tells us that the universe must have certain properties, including the ability to form stars and create the elements necessary for life. Galactic graveyards are thus essential to our existence. In our journey through galactic graveyards, we've explored planetary nebulae glowing with the last light of dying stars, supernova remnants expanding through the interstellar medium, neutron stars spinning hundreds of times per second, black holes from which not even light can escape, streams of stars torn from dwarf galaxies, and the diffuse enriched gas pervading all of space. We've seen how these remnants are not mere endings, but essential parts of cosmic cycles that have created the chemical elements, shaped the evolution of galaxies, and made possible the existence of planets, life, and consciousness. Galactic graveyards are places of transformation where stellar material is recycled, where extreme physics challenges our understanding of nature, and where the past and future of the cosmos intersect. Every atom in your body passed through these graveyards on its journey from the Big Bang to you. The oxygen you breathe with every breath was forged in a massive star's core and scattered when that star exploded. The iron in your blood was created in a supernova's final moments. You are intimately, physically connected to these cosmic deaths and rebirths. As we look to the future, our exploration of galactic graveyards will continue to reveal new wonders and deepen our understanding of the universe. New telescopes will discover more distant and exotic remnants. Gravitational wave detectors will reveal the violent mergers of compact objects throughout cosmic history. Computer simulations will capture the complex physics of stellar death with ever greater fidelity. And perhaps most exciting, we may discover how life emerged from the chemical crucible of successive stellar generations, and whether we share the universe with other forms of life built from the same stellar elements. The story of galactic graveyards is ultimately a story of connection and continuity. It's the story of how simple hydrogen and helium, created in the Big Bang, have been transformed through billions of years of stellar alchemy into the rich diversity of elements that make up the world around us and within us. It's the story of how destruction leads to creation, how death enables life, and how the universe perpetually reinvents itself through cycles of stellar birth and death. As you gaze up at the night sky, remember that the ancient starlight reaching your eyes began its journey from stellar furnaces long ago. Some of those stars have since died, becoming the very graveyards we've explored. Their light continues to travel through space, carrying information about their lives, even though the stars themselves are gone. And scattered throughout the darkness between the stars are countless invisible remnants. White dwarfs cooling in eternal night, neutron stars marking cosmic time with metronomic precision, black holes lurking unseen, and vast clouds of enriched gas awaiting their turn to form new stars and planets. We are fortunate to live in an era when technology allows us to study these phenomena across the electromagnetic spectrum and through gravitational waves and neutrinos. We can peer into the hearts of supernova remnants, watch as black holes merge and space-time rings like a bell, and trace the chemical elements from their creation in stellar cores to their incorporation into living beings. We stand at a unique moment in cosmic history, able to understand our place in the grand story of matter's journey through the universe. The journey through galactic graveyards is not just a tour of astronomical objects, but a deep exploration of our origins and our place in the cosmos. These are not distant, irrelevant phenomena, but the very foundations of our existence. Understanding them helps us understand ourselves and our relationship to the universe. It reveals that we are not separate from nature, but intimately woven into cosmic processes that span billions of light years and billions of years in time. Thank you for joining me on this extensive journey through the galactic graveyards. From the delicate beauty of planetary nebulae to the violent explosions of supernovae, from the bizarre physics of neutron stars to the ultimate mysteries of black holes, from streams of tidally disrupted galaxies to the diffuse enriched gas pervading all space, we've explored the many faces of stellar death and recycling. These graveyards are not places of sadness but of transformation. Not ends but beginnings, not death but metamorphosis into new forms and new possibilities. As you go forward, carry with you the knowledge that you are made of star stuff, that atoms forged in ancient stellar furnaces flow through your veins and enable your thoughts. Remember that the universe is a place of endless transformation, where nothing is truly lost but only changed in form. And look up at the night sky with new appreciation, knowing that scattered among those points of light are countless invisible graveyards, the remnants of stellar deaths that have made your existence possible and continue to shape the evolution of galaxies and the universe itself. The cosmos is vast beyond comprehension, ancient beyond imagining, and filled with wonders that challenge our understanding and inspire our curiosity. Galactic graveyards remind us that even in endings there is beauty, that destruction leads to creation, and that we are participants in a cosmic story billions of years in the making. This is not just astronomy or astrophysics. This is the epic narrative of matter's journey through time, and we are privileged to be able to read and understand parts of that story. May the knowledge gained from studying these stellar remnants continue to inspire wonder, drive scientific discovery, and deepen our appreciation for our place in this magnificent, ever-changing universe.